for this you should have your NGSolve up to date. Our current recommendation is to make it simple with pip installers. Either you do pre-versions or you do release versions. Either you want to have a daily new version or you want to have a new version every second month. You can check it. I think most of you have done this already. So when Edoardo is start in a minute, you can follow with the same tutorials, going slowly over it, so you can try it yourself. So it's getting used to the software, getting used to the menus. That's a goal for today. So it's a part of introduction to finite elements, but we assume you know finite elements, so this is very brief. The focus is how to do finite elements within the software.
And you need to know also a little bit of Python. But
so then let me shortly introduce Edoardo. Edoardo is a PhD student here at Wien, and he was doing the exercise class with a big class of CSE students, and he knows very much what it takes to get the 50 students working with NGSolve, and a lot of difficulties at the beginning, and he came up with a lot of nice fancy exercises for the students. Some of them are included here. And I think now Edoardo will show you either first steps with NGSolve or update some new features.
Oh, no, thank you very much.
We have time today, so we're in a relaxed speed. Whenever you have questions, problems,
raise your hands if you have questions. And okay, thank you very much for the introduction. So we should
it's good that if the speaker knows to whom he's talking to.
So can you please introduce yourself, like first name, last name, and then what's your field? Okay, if you're an engineer, if you're a mathematician, if you ever worked with NGSolve or not. Okay, can we start from here and then zigzag around? All right.
So I'm Edoardo, I'm a PhD student in mathematics at the University of Trento, and I'm using NGSolve for a while now, and mostly for finite elements for time-dependent PDEs.
I'm Wouter. I'm a PhD student in the Department of Mathematics at TTH Zurich. I've been using NGSolve for a couple of months, almost a year now. Actually, Nico introduced me to it. So yeah, I work mostly on numerical methods for PDEs, load analysis, and implementation.
Hi, I'm Ellen. I'm PhD student at the University of Twente, and I've been working on NGSolve for about a year, and I'm working on some numerical methods for PDEs.
Hi, my name is Natalia, and I'm a master student at TU Wien. I am currently involved with the computational science and engineering, and I have just completed the non-PhD lectures with a professor and the teacher.
So we really see the basics today.
Martin?
Hi, my name is Martin. I did my PhD here at the TU Wien. At the moment, I work at the fiction and links, and the main focus of work are lyrics for time harmonic.
Hi, my name is Madeline, and I'm a PhD student in mathematics. I'm from France, and I'm using NGSolve for like a couple of months now for some PDE techniques.
Hi, I'm Sebastian. I'm from the TU Wien, did my PhD here, and I'm in computational biomechanics, so we are concerned with continuum mechanics and so on. I want to use NGSolve for teaching in the next semesters, and personally I'm also interested in like meshing and continuum mechanics.
And you've been using it for around?
I've not used NGSolve directly before, only implicitly in FreeCAD or in Gmesh.
Okay,
so
perfect.
That's my expertise of NGSolve.
Yeah, good.
Hello, my name is Wien. I'm a PhD student at the University of Rostock in Germany. I'm doing my major in electrical engineering. So I do more than a year to sell electromagnetic spotting.
Hi, I'm Hannes. I'm with BMW in Munich, and I'm in the traction motor development group. They're quite new to NGSolve. I tried it like a year or 2 years ago, and now I started.
Hi, I'm Tim. I'm a PhD student at the University of Göttingen. I've been using NGSolve for 4 years. I've been for everything that comes up PV related.
Okay.
Yeah. Hi, I'm Johan. I'm a master student in Göttingen, and I'm currently working on NGSolve as a student worker.
Hi, I'm Maximilian. I'm a bachelor student of computer science, also in Göttingen, and I'm working for some courses with NGSolve, and I'm also have developed something in this.
Okay.
I'm Philip. I'm an assistant professor in Fanta, and I think I'm using NGSolve since my bachelor thesis, so a little bit more than 10 years.
Okay.
I'm Paul. I'm a postdoc in Vienna. I've been using NGSolve since my PhD, which is really quite some time, so 6 years probably. Yeah, and mostly to implement several things, but also some bets.
Hi, I'm Thomas. Qualcomm in Munich. I'm using NGSolve for mainly microacoustic simulation, so wave equations and harmonic wave equations. I'm using NGSolve since 3 years.
Yeah, so I'm essentially the same user. So it's Qualcomm in Munich. I think we have been using NGSolve for 15 years, 20 years, I don't know.
It must have been in Sangenmeyer, yeah?
Yeah,
it was in 2006, and so 20 years.
A long time. So I'm mostly maybe not quite up to date, and I'm interested in what you do with this.
Okay.
Yes, I'm Christopher. I, together with Matthias and Joachim, founded the Spin of Perception, and we're mainly trying also to stabilize, but also building this ecosystem of NGSolve and bringing it more into industrial applications. So the research stuff that Joachim does, bringing and for also since the bachelor, so 10, 12 years in NGSolve development.
Yeah, so for me it's the same. So I started really developing on NGSolve 10 years ago. I was part of the NGSolve team, and not to miss.
I'm Jay, and I have been using NetGame since 2000. I was a beginner then, and I still feel like a beginner now.
You're from?
Say again?
You're from?
Portland, Oregon.
Hi, I'm Vadim. I'm from Latvia. Company Sivas. We develop a software for engineers, and we are using NGSolve engine internally for a couple of years now. Yeah.
I am Jan. I'm a PhD student. I'm using NGSolve since 4 years, and mainly now for the simulation of compressible flows.
Hi, I'm Christoph from Göttingen. Using NGSolve more than 16 years, I guess, roughly. Typically, I've also was involved in last year's meetings and didn't follow it like this time I relax.
He's sweating already.
So we have all seen this I tutorial. So section 1 is maybe Jay, and section 3 is maybe Christoph. So they have certainly seen right up.
So, I'm Edoardo Bonetti. I'm a PhD student of Joachim Schober, and I have been teaching this semester NumPD. We developed together some exercises with Jan as well. Thank you, Jan. And yeah, so I understood what was complicated to understand in NGSolve, and I tried to repropose it today for you to better understand it. And obviously, still, if you have questions, please stop me, ask me, especially in the first 2 tutorials, okay? And you presented yourself, right? You introduced yourself? Okay, then. Okay, should we start then? Okay, great. Okay, by the way, one thing that we want to try for you is to install NGSolve and maybe try to run the first scripts and we can run them all together, and then obviously if you want to follow, you can follow, otherwise you can go through and run the exercise or the scripts together. If you don't know how to download them, there is this, what is it, the zip at the top of the page, okay, that you can download, or you can go at the top of the page and download it as a MD or dot, well, let's go into a runnable one and then I can show you. Is everyone done with the installation, by the way? Yeah? Or if you have problems, please tell us that someone can come and help you out, okay? Okay, so let's first maybe show you what's possible to do with NGSolve, and yeah, we can run it together maybe. Okay, let's go. I will not talk about this example or how to implement this as example yet, but I will talk about can you see me in this way? Yeah. I will talk about what you can do with NGSolve. So for example, let's suppose that you want to simulate an elastic pendulum. Okay, you take a pendulum, we fix it, so you fix only the average position of one side, and then you twist it. Okay, you put it I don't know, in vertical position and you let it fall. Okay, and you see that it should swing and should wobble a little bit. And let's run everything together. So when you import the NGSolve, you create your, or you need to know from the theory what to implement. You create a certain geometry, you mesh it, you give some names. Yes, maybe if I put it down here. Okay, you mesh it, and this is the geometry. Here down is fixed. Okay, it's not fully clamped, so it has a it can move around. And okay, let's go. We define things that at the end we will understand what's going on, but let's go at the example at the end. And here is the final simulation. Okay, so you see that it should stay. So let's say that it starts from an undeformed position, and then gravity is switched on, so it starts to bounce a little bit, and then it falls down. And you see that yeah, it's nonlinear elasticity, or the theory of nonlinear elasticity is applied here. Okay, this is a new whet the appetite that we have seen already. Okay, last year's. Okay, so for today's introduction, there's like it's split into different parts. The installation, but we are done with it. Then we see the basics of NGSolve. This is going to be the slowest one, especially number 1 and 2, the Jupyter notebooks. Then we speed up a little bit. We can have a little break here, so just for you to know. And then we go on to the complementary things. That this is important stuff that you should know that it exists, but we will not go into details. And then finally, we have a look into the advanced topics. Okay. The advanced topics is the core of NGSolve, is why it is useful to use it. Okay. And then at the end of the tutorial, we go back to this example I just showed you, and we are able to understand step by step what's going on. Okay, so let's start with the first example. Okay, so the first example. By the way, so all of you know finite elements, I guess, right? So you know how they work, and they can be split in four different parts, or in 4 different steps. First of all is to define a domain, okay, and to mesh it. The second step is to create your finite element. So for example, we can work with Lagrangian elements or Ravier-Thomas elements, etc. We need to reserve some storage for our solution. So that's why maybe when you implement something in C++ or in Fortran, you need to create vectors and matrices, etc. And you need to take care of that part. Here you don't. It's already implemented. And okay. Then you need to create, or we need to create a linear and a bilinear form. It would be great to create them in a symbolic way, so that everything is done automatically. And we need to assemble them in the end to have actual objects that we can invert. And then the last thing is to actually invert the matrix, so to solve the linear system. And here we may need to take care of some homogenization techniques. Okay, so unfortunately the first example needs to be done on the unit square, but then we see what to do with other geometries. Okay, so the problem that we try to solve today is the following. We have the usual Laplacian problem. The right hand side is going to be 20 times x times y squared on the domain, and then we have some Dirichlet boundary condition, homogeneous Dirichlet boundary condition, and then we have some Neumann homogeneous Neumann boundary conditions. In particular, we have a Dirichlet on the bottom left, okay, and the homogeneous Neumann on the top right. Okay, so let's basically do the same steps that I told you before, the 4 steps plus the step 0 on Python. Okay, so step 0 is going to be to import everything. If you know the package, obviously you can import only the things that you want to import, but for now let's import everything and we run it. Let's run it together. Okay, so it's done. We need to define a domain. In this case, it's going to be the unit square. Fortunately, as a test, NGSolve gives us already a unit square and a unit cube, so that you can try your implementation immediately. And okay, this is unit squared. You generate the mesh. The mesh has a certain mesh size, and then we pass the mesh onto a netgen mesh, but more on this later. And we draw it. Okay, so this is great. We can turn it around. We can look at each element how it's called. So for example, if you click on it, you have the left hand side is called left. You have some numbering of the edges, so if you need to do something on the edges, you can. And then you can click, you said this is space 0, etc. On the top right of the web GUI, by the way, this is called web GUI, you have an open control that you can use to interface a little bit with this command. So you can turn off the axis on the bottom left. You can see them, that they disappear, and then the edges, and then the wireframe, and then the surface, and you can activate them, but play around with and you understand what's going on. Okay.
Web GUI was mainly implemented by Matthias. It's done since, I think, 4 years. There are some questions, some wishes to web GUI. Matthias, what was it said?
Also, if someone has troubles installing, since still now, just point it to me and that will come.
Oh, by the way, this thing here you can download as I showed you before, and you can try to run it. Okay, just if you want to. Okay, so this is the first step. The second step is going to be to define our finite element space. To define our finite element space, we need 2 things. We need the mesh, and this is mandatory. And the second thing is to define the Neumann boundary, the essential boundary conditions. Obviously, the essential boundary conditions here will be called or are called Dirichlet, and you pass them using this. Is it pronounced regex or regex? It depends. I don't know. I heard both, but okay. This regex expression. Okay, so basically you define a name and then united and then another name, and basically it tells internally to NGSolve that those are the two edges that needs to be Dirichlet or with the essential boundary conditions. Okay, so run also this one. Okay, moreover, I told you that we need to reserve a little bit in advance the space. It's not true that it is in advance, but just to go through the, you will see different approaches, but let's reserve also some space for the final result. Okay, this is going to be a grid function. This grid function needs to know obviously the space. Yeah, that there is not much more to say about those. The only thing that I can tell you is, first of all, that you can query them. So you can open the help and obviously run it and see what's going on. So the grid function is a coefficient function, and this is going to be quite important in the upcoming notebook. And the second thing that I can tell you that is quite important is that you can visualize the reserved space or the reserved memory. In this case, it's going to be a vector of zeros because we did not initialize it, or is automatically initialized to 0. Okay, so this is the grid function. All right, so third step, we need to define somehow symbolically our linear and bilinear forms. To do that, we use something that are called proxy functions. In general, proxy functions, they need to, or there are two proxy functions. One is the trial function and the other one is the test function. To define them, you just need to say finite element space. So you need to know the finite element space and then dot trial function and then or dot test function, okay? Or if you know what to do or what you're doing, you can use this one-liner. So UNV and TNT dot test.tnt. Let's read it. Okay. To create your bilinear form, so remember that you need to create the gradient and then inner product and then the other gradient. You just need to say bilinear form and then add gradient u times gradient v. Internally, it not know what it does, what it's doing. To specify that is an integration over the volume, you need to specify times dx. Okay, this is also quite important. We can run it and we can assemble it at the end. In particular, if you print it before the assembly process, it tells you, hey, there exists no assembled matrix because we did not reserve some space for the storage yet. If you run it afterwards, you can print the actual matrix, and this is the matrix. Okay, this is a row-wise storage. Should be row-wise storage matrix. CSR. Okay, so oopsie. Okay, so this is everything that you need to know to define this bilinear form. The symbol dx, I don't want to go into the specifics, but is a differential symbol, okay, and it acts on the volume. Is predefined in NGSolve. You can, I think that you can click on it, and it should so go to definition, and it should give you the definition of what is this symbol. This is what.
Why do we have a master and the bilinear?
What is this? Sorry, let's go back. Ah, this one. Yeah, good to point out. No, I was playing around before with the. Yeah, sorry about that. So okay. So for you at home, I don't have one term. We will. It's correct, right? In the.
Yeah.
Is it without?
No, it's also in the tutorials.
With.
It is also there is the master motion.
Well, nothing changes. I mean, it's just a bilinear form, just to show you that something. Consider it without. We will push the correct one, the updated one, or delete it. Yeah. Okay. So thanks for pointing it out. Okay. So okay. Let's run it without, so we can visualize something slightly different. Alrighty. So what about the right hand side? Or do you want to say no? Okay. What about the right hand side? Well, in the right hand side, I said that we need to define 20 times something. This 20 is just a float, okay, and or an integer, and then times x and y. They are already objects that are already known in NGSolve. They are special coefficient functions. In particular, they are coordinate coefficient functions, if I'm not wrong. We have 3 of them by default, so x, y, and z. And you can treat them basically as any other function. So you can take I don't know, the product, take the exponentiation, and yeah, the power. And okay, so just let's run it, and then we can obviously, after the assembly, you can print the vector. Okay. In the particular case of linear forms, you can print the vector even before running the assembly process. because maybe you know you need to have a, I don't know, a 0 right hand side. So okay, so this is done. Okay, so and finally we can solve our linear system. This is, or it's understood as a separate step, in the sense that you can do a lot of different things. You can use a direct solver, you can use an iterative solver, so that it's good to differentiate a little bit. One flag that is important to keep in mind is the following: Friedhofs. Okay, so what this thing does is to know the fact that you have some degrees of freedom, as you know, and some of them they need not to be touched. So in this case, you touch only the degrees of freedom and you invert the matrix only if they are not along the Dirichlet boundary. Okay, so the Dirichlet boundaries are not Friedhofs. Yeah, and that's really it. And then you multiply the inverse times the vector, and you can store the result in the grid function. One thing that I want you to notice that here we use gfu.vec.data, and this is to change the value of the vector. Okay. Yeah, please.
So we once tried to use this on a matrix that's not like well posed.
Okay.
And somehow it gave a solution that looked okay. Is there some way you deal with this? Or is this system lucky?
The matrix is not what?
Not well posed. So we had, let's say,
singular matrix.
So it was like Stokes, or if you have like
an indefinite matrix.
Yeah, it's like you have like a block of well posed and a block of zeros.
So the whole matrix is regular.
No, the whole matrix is singular.
So when the matrix is singular, then the inverse should complain about it.
But it did actually output basically, like it was like Stokes, and we didn't enforce the average of the pressure. And then
it's randomly, it depends on round-off, so
okay.
And it depends on what kind of direct solver you're using. So Umfbach and Paradiso and Paskoletsky depend differently. Some complain about that the matrix is singular. Finding out as a matrix is singular is also not well posted. Some survive from. So you should know that to have a singular matrix, and you should not do it. Sometimes it works.
Yes. By the way, I changed the bilinear form and I put a mass matrix because I wanted to play around at first and to change this inverse and to take it without the Friedhofs. That's why. So if you have an invertible matrix and you know that it's invertible, that's the explanation why. Okay. But so far I think it's clear, right? Or do you have questions? No? Okay, then we run also this thing, we invert the matrix, we store it in a GFU, the grid function, and we can visualize it. And here we can open the controls and do many different things, such as autoscale, don't consider the autoscale, number of colors, but in general we can focus for now on this specific fact that if we deform it, then we have such a solution. And such a solution you can notice that is made up of linear polynomials. Okay, so this was linear polynomials. So this is good. This is how to solve a problem quickly. In particular, before I told you that the mandatory keywords or the mandatory flags that the H1 space needs is just the mesh. Okay. The other important is or one that you will use a lot is the order, and if you change, for example, the order to 2 and you rerun everything, just do like this, and you go back at the end, you can see, first of all, you notice that now the vector is quite long. The fact that at some point you will see that the values drop to, I will come later on to the fact that why it is this long and how the degrees of freedom are spread on the grid function, but or on they are saved internally. But the important thing is that now we have our result, and our result is much smoother. Okay, so deformation, you can deform it, and if you have a good eye, you can see that this is second order polynomial. Okay. All right. So as last thing that I want to tell you is how to interact with NGSolve. There are many different ways to interact with NGSolve. One is to create a script in Python and just run the script. If you want to know the energy of something, just type Python or Python 3 and then the script and you have the result. If you also want to visualize it, you have to remember to use NetGen. Okay? Or, yeah, that's really it. Or else you can use the Jupyter notebook as we did so far, and we can add this last line. So import netgen.gui. Obviously, you don't need to import also the web GUI because that's, and automatically it opens up the GUI that was created for NetGen.
Yeah, in the last millennium.
So
let me ask, how many of you are using this in Jupyter and with the web GUI right now?
That's Visual Studio currently.
Visual Studio, Visual Studio notebooks, yeah. And from the, I said, who uses Visual Studio or conventional Jupyter?
Okay.
Yeah. And someone uses the old NetGen GUI?
Okay, good. Okay. The separation of people. Okay.
I'm using usually now Jupyter, and when I do set up things, I go into the NetGen GUI.
Let's see if it works right now. Hopefully it does. Can you just run this one, right? It should. And this window should pop out, and yeah, we have the same thing as before. If I also recreate the solution, it should pop out the solution. The solution should pop out. Okay, good. So this is the first example. Let's try to, by the way, can you also click on things and go to the definition from your VS Code? So if I go to, I don't know, let me see, to the draw, and then I go and I click go to definition. Can you go to the actual definition? Yeah? Because this is quite helpful when you start with NGSolve, no? So the reason you can use it, right? Okay, if you don't, you can go onto the main page, and there is, at least for me it worked. Is it here? So if your Pylance does not recognize NGSolve, you can add these few lines to the in the settings, and then it will be recognized. Okay. Okay, so let's go back to the. Okay, let's talk about now something important, that is the coefficient functions. So NGSolve, as we saw, it's full of coefficient functions, and they are quite important, and a lot of objects are defined upon coefficient functions. We will see how to define them, visualize them, evaluate them, look at the expression tree, so how they are stored internally, integrate them, so this is quite important for engineers and in industry, I guess, differentiate them, look at the parameter coefficient functions, and they will be very important in the end, especially for time-dependent problems. Interpolation, vector valued, mesh dependent, and how to compile coefficient functions. Okay. So
let me the coefficient functions in the 2000 version of NGSolve was only the coefficient function in front of gradient u, gradient v, the lambda, gradient u, gradient v. So the name comes from this coefficient function. And from year to year, the coefficient function got more and more powerful, and now all the functions are keeping the same name, coefficient function. If you want, by called coefficient function.
So today there is also a little bit of history. Okay, so import everything for now. Still, we work on the unit square, but which will change in the next or upcoming notebook. Okay, so define a coefficient function. To define a coefficient function, you can start from previously defined coefficient functions. In this case, I told you that x and y and z are coefficient functions. Some algebraic expressions, and then you can visualize what they are. So this is, again, a coefficient function. Okay, good. So far, was good. We can try also to see what is just x, okay, and still this is a built-in coefficient function, nothing special so far. To visualize them, we basically want to visualize it on a mesh, and you can only visualize coefficient functions on a certain mesh. Can you visualize them also on shapes? No, no, right? No. There is a feature for next year. No. Okay, so let's run it. And what is this? Well, this is, as you expect, a parabola. Okay, an inverted parabola. It has 0 values on x is equal to 0 and 1 minus x is equal to 0. So x is equal to 1. And yeah, and also here you can play around with. You see that the solution is quite smooth. So it's not a solution. This is smooth because it's not a solution. Let me rephrase it. Okay. One important thing that you can do, or you may need, is the evaluation of a certain coefficient function on a certain point of the mesh. To do so, you need to pass first a point to the mesh, okay, so the first line, and you create a mapped integration point, and then pass this mapped integration point onto the inside the function. Okay. This is a two-dimensional object. If you were to work with a three-dimensional object, you need to add, I don't know, 0.1. Okay, it's still in the unit cube. It's fine. What if you go out from the unit cube? So I don't know, let's say 2, and you can try to run it, and it complains. So you should not go outside from the mesh. Yes, please.
What happens if I try to evaluate the discontinuous coefficient function on the the edge of two different elements?
Kind of. Okay, so this point is not necessarily a vertex in the mesh, it's an arbitrary point in the mesh. And the first instruction says mip equals mesh of this coordinate. It searches for an element containing this point and gives you the reference coordinates within this element.
Okay, so it's
and it's random which element it finds first containing this point.
Okay, I see.
Okay, so let's go back to 0.2. Okay, good. Okay, so for example, you can also take a function and try to examine it point by point. So in this case, we are in the unit cube. We move on the y direction of 0.2, and then we evaluate at 0.0, 0.1, 0.2, etc. And let's run this thing. And this is how it's done in a Pythonic way. Okay, with the zip. And yeah, so it gives out the results that we are interested in, and you can see that the shape is like the parabola. You can also use the vectorized version, so you can run using NumPy. So you create 2 NumPy arrays, you pass the arrays onto the mesh, and it knows what to do. Okay, so this is the result. This is an array of the correct solution. Okay. Okay, so let's for example, you can also you can plot it. This is okay. So you can also plot it and see if the desired function is correct. Okay. All right. So at the beginning, I told you that there is this let's go this expression tree. The expression tree is how internally is the coefficient function is stored in NGSolve. And for example, let's pick our favorite function, x times 1 minus x. And internally, you should think about this function as if it were a tree. Okay, so you start with a node, and the node is this operation, is an algebraic operation x. And then you on the left have the other operation that is just the function x, and on the right you have another operation. So basically you start to grow. Let's print it, and in fact it's exactly what I told you. Okay, so you start and you have this first node, the operation x, times, okay, and then you have x, and then the other operation minus on what, etc. And obviously they can become quite large. Okay, so, all right, so this is how it's stored. The second thing that you need to do is or you can do is a more advanced thing is an integration. In this case, you pass a function. You pass the mesh on which you are interested to integrate, and then the order of integration, and then you can run it. And if you run it, you have the result. That's it. Nothing really special. Something that starts to be a little bit special is the automatic differentiation of a coefficient function. So if you have defined your coefficient function using, for example, the x as before, you can say, hey, let me differentiate with respect to x. And what it does, it goes through the tree and differentiate every time it finds the tree with the common rule of a differentiation. So if you have times, then you use the Leibniz rule, and you keep going. Okay. Okay. Let's. Do you want to add something?
No.
Okay. So. Alrighty. So in this case, before we had a parabola. If you differentiate a parabola, we have a plane, and this plane you can open, deform it. Looks good. Okay. So as I told you, you can recognize inside the inside this new tree the automatic differentiation, right? So you have a plus before you had a minus, and then these two other things. Okay. Okay. So far amazing. We can do the basic stuff. Now it gets a little bit more interesting. At first it doesn't look like, but you will realize that it's something powerful. So let's talk about parameters. Parameters are special coefficient functions that keep track of their value, and the value could be somehow changed in the future. So let's start with k is equal to 2, okay? And k basically is the frequency of this sine wave, and we draw it, and we draw this sine function, and this sine function basically is something like this, okay? So you can recognize that this is going to be a sine somehow, okay, a sine wave. And then the idea is, what now if I want just to change the value of k? So I set k to 10, and then I can just redraw f without re-evaluating like the whole process, and it changes the value. So this is something that is quite nice. And what is the magic behind how this is done? Well, basically f takes into consideration that inside this expression tree there is this parameter coefficient function. It's a double is real, so yeah, that's on the surface. And also something that is quite interesting is that you can take the differentiation with respect to this particular coefficient function, and you can run it, and you can see that differentiation does what it does, and you can integrate the differentiation knowing the exact solution, and the integral or the error is 0, so it's an exact differentiation. Okay. Okay. So questions so far? No? Did you try to run the script and it works? Okay. All right. Okay. The interpolation. Okay, let's talk a little bit more on the finite element point of view. Obviously, we have all these functions. One important function that is a coefficient function is the grid function. Per se, the grid function you can give a specific an interpolation of a continuous function to a grid function. So you pass our parabola onto something that is defined only on the vertices, okay? And you can draw it, and you can see that the draw is something that is a first approximation or a first order approximation of this function. And yeah, that's all you need to know for the set. Well, there is a little bit more to add. So the magic behind this set is the following. You need to take your grid function, you need to zero all the entries, and then you do a projection onto each element, an L2 projection on each element. And then you have 2 degrees of freedom from 2 sides, and you average the degrees of freedom to have some conformity, okay? And these things work also with other finite elements. So, for example, for Ravier-Thomas. And
so this was the original one. It just needs some shape functions. You don't have to implement degrees of freedom for this. You just know how to evaluate shape functions and do L2 projections for this. And later came interpolation also.
Yeah. And there is something that is a flag that is dual is equal to true. I will not explain it today. If you want, you can watch Jay's talk on the how to do the dual, to take the dual of or the dual projection, let's say, or the dual set. And in that way, you have an exact interpolation on the vertices. Was it Jay? Was it you talked last year about? Could be Jay. Could be Jay. Okay. Okay, then we run it. Yes. Okay. So quite quickly, how to define grid functions for or a vector valued grid function. At this point, you just pass a tuple. Okay. In base of based on how long is this tuple, you have a certain dimension for your grid function. Sorry, for your vector valued function. You can if the name coefficient function is too long, you can use the shortening CF. And you can run it. So CF works as well. You can draw it. You can draw the vectors as well. Otherwise, you can open the controls and select the vectors yourself. So, by the way, so where are they? Okay, so you can select vectors. You can select which part of which entry of the value of the vector to visualize. So the 0th or the first or the norm. And as last thing that I want to point out, and this is something that students didn't get it immediately, is that if you deform a vector field, it does not deform going up, but it deforms in the direction of the vector field. But this is one way of visualizing it. So in particular, we have this function here, and if you visualize it, stays on the plane, but it deforms in this way. Okay, it makes sense in the end. All right. Something else. No, obviously, like you can derive it automatically or using just the grad function, and you can visualize the derivation, and obviously is a piecewise constant, and you can see that this is piecewise constant. Something that I want to point out: if you apply the grad to a grid function, as a result, you have a coefficient function, a generic coefficient function. Therefore, you need to visualize it using the mesh. Okay, the mesh flag. Otherwise, it will complain, saying, "Hey, this is a coefficient function. I don't know what to do." Or we can just run it and see, like, you cannot draw a generic coefficient function. Okay. Also, this one is something that is quite a typical error. Okay. Okay. So far, all the basics of the coefficient functions are done. One thing that you could be interested in is when you model a certain domain and you have some prescribed potential or a prescribed flux on the whole domain or on the boundaries, you can use some mesh dependent coefficient functions. So for now, let me just create a grid function and just create a geometry. Okay. We gave some names to the geometry. This is inner, this is called outer, this is called shared, wait a second, shared, and this is called, again, outer, no, this is non-shared, okay, just 4 random names.
You can plot the edges also thick if you have difficulties hitting them, as I already said.
And, yeah, but about the drawings, I think that later on we will see a lot of different drawings with nice styles, so. And here you can, for example, create a coefficient function that has some different values on different domains. How to do that? You basically create a dictionary with the prescribed names and the prescribed values of the coefficient functions. And you just say material you give the name and then mesh, so it needs to know the mesh or on which mesh, that dot material coefficient function and pass the dictionary. And you see that this thing is created, okay? So you have this funny hat, and that's really it. How to create domain coefficient functions. How to create boundary values coefficient functions. You just say mesh dot boundary coefficient function CF, and then the value. So as before, a list, and then the default value. The default value is the value onto that is not here. All the edges that are not here, or all the boundaries that are not here. Okay. So let's run it. One more thing that I want to point out: when you do set, you also can define on which part of the mesh you want to project or to do the set, and yeah, so you can specify it defined on, and then the name of boundaries or name of. I think that here you can, if you had a third dimension, you can say B boundaries, right? So basically you call it B, B boundaries. And this is the boundary of the boundary. Yeah. Okay, so we run this thing, and this is as well something that is defined like this. You see that this lives more or less only on the edges, and somehow there is an immediate extension inside the domain, and that's it. And this is useful. Okay, so last thing that I want to point out is the following. Yeah, please.
Yeah, so you have a GFU.set and you also have GFU.interpolate. Is there any difference between them?
The set with dual is true is more or less the same as the interpolate. So the interpolate uses the degrees of freedom. This is point values or integrals over edges. The set does the L2 projection on the element. The set does not need an implementation for dual shaped elements, which came in maybe 3-4 years ago. That's one thing what the interpolate can do if you have points, if you have an integration point coefficient function. It's a need for elastic plasticity simulation. Then you have only the interpolate but not the set.
Okay, so dual equals to true. You see that it changes the value, okay, and okay, the value now are quite are precise. So this is -2 and this is 0.25. The values that we expect. If we just say this thing here, this is -1.9. So no, this is not an exact set. Does not an exact interpolation, but a good enough one. Okay.
As an example, when you have a square, you interpolate the function x squared, for example, into linear finite elements. The function on the right edge is 1, but with the set you don't get the 1 exactly. With the interpolate you get the values in the vertices exactly 1. People are complaining about the set and they don't get the exact value 1 on the right edge.
Another question.
Yep.
On the boundary, can you plot the boundaries here? Or not you can. I'm asking about what it yields really.
We should not be able to plot the function itself, I think.
But
because it would be a one-dimensional plot, and the one-dimensional plot I don't think is implemented in the draw function. For you works?
Yes, it works. Can you just try it? Because I'm curious about it.
Yeah.
Yeah, it does something wrong.
Matthias, what do you guess? Does it blow?
We have
it blows something wrong. Like the information makes
draw,
sense, but then
and then this one.
Yes.
Okay, let's try it out. Yeah, it does something wrong. It does something wrong, but like in the sense that it doesn't.
Okay, yeah, I can. This to make if it's a material coefficient function or a boundary coefficient function, the result does not know whether it's indexed by the boundary index or by the material index. So now the index is taken by material index, also it was created as a boundary. He has it on the list to 1, or if we don't allow it, then we are breaking a lot of code if we change this.
Okay, but okay, good. All right. Yeah. Okay. So compiled functions. I think that most of you already used compiled functions. So let's quickly. What it does is the following thing. So we have these huge 3-4 huge functions. Okay, and the idea is that we traverse for trees. Traverse. we traverse different nodes, and we can traverse them many different times. So the thing is, can we linearize this process and traverse them maybe just one? And indeed we can. So we create my function compiled, and we just plot the function, and we print the function compiled, and you see that the object is two different things. Okay, so the first one is a tree, the second one is a linear program. Or maybe we start, let's go through what it does. Takes a point, okay, coordinate x, and then at step 1 it takes 1, and then the second step it is use the operation minus onto the step 0 and onto the step 1. Okay, so creates the right hand side basically of the operation, and then the step 3 is to use the operation times between what's going out from step 2, so the right hand part, and step 0, so x. Okay, so this is an actual program.
It's an upper one, you find x twice, so x is evaluated twice. But here you find x just once, and it's just evaluated once.
Okay, so let's okay, so for example, this is the creation of a big function, okay, with a huge tree. And here what we do is we create final and final compiled, and we just take a look at how long it takes to do the integration with order 10. And it should be okay, 7.9 milliseconds and 500 600 microseconds. So the difference is around I don't know, 11. Okay, so it's 11 times faster in this case, and we can look at what's going on in the behind. So we had this very bad looking function, and if we print it using the compiled version, we can understand what's going on in 25 steps. So in 25 steps I can give you the value of that function at that specific point. Meanwhile, if you want to evaluate the function at a specific point with the tree, you can go down and do a lot of different things, and the tree has more than 1,000 nodes. Okay, that's why it's a little bit faster. Okay, yeah, and then VS Code complains a little bit and tells me stop. Okay, that's it for the coefficient functions. Do you have questions? No? Okay. All right. Finally, we do some modeling of the domain. So let's. Have you ever used the Open Cascade? Or I know that there is someone that is expert in Open Cascade. Okay. So you used it, right? Okay. So what is Open Cascade? Open Cascade per se is a software that is written in C or C++, mainly C++, and it's quite useful to model difficult geometries. What is going on is that netgen, so the measure that onto which NGSolve is based, or that the NGSolve use this mesh quite a lot, or they're very much integrated, decided to create a wraparound OCCT, and in this way we can use all the functionalities from this package with just some simple Python commands. Okay, then we go through what's going on right now.
It's open source, yeah.
And it's open source, obviously.
Yeah.
So, okay. Okay. So we just create, we have a wrapper around the OCCT, and this is the wrapper, okay, in this module, netgen.occ. Okay, so we run it, we import everything, and the first thing that I want to teach you, so we will go through 2D objects to the 3D objects. We start with the 2D. Do we have a paper sheet? No. Okay, so the idea is the following. To sketch things in a hyperplane or in a plane in 3 dimensions, it would be better to sketch it on the table and then to map it. Okay, and this is the idea of work planes. So you sketch it in 2D and then you map it in 3D. Obviously, you need to predefine everything. So you need to define a point into space, and so where to our plane is going to be mapped. And but let's see an example that may be a little bit easier. So we create our work plane using work plane, this class work plane, and then onto the work plane we create a rectangle that is spawned at a certain point and has a length of 2 and a width of 5. Okay. So this is, we try to run it. You could try to draw it, but it complains because so far it's going to be just this topological abstract object, and we need to declare what things about this object needs to be extracted. In this specific case, we need to extract the face. Okay, so we set the face, and we want to draw it, and we have this rectangle. You click on it, it has no names. The names are all default. So far we have created only one rectangle. As I told you, the class work plane needs a few things. So the first of all, it needs a pair of a set of axes. Okay, what is the first name axis? This is a point in space and basically a triple of directions. In particular, you don't need to give 3 directions. Why? Because you have the point, you have the normal direction of the plane. Okay, and then you need to give a principal tangential direction or horizontal direction. As a second thing, you need to pass a 2D axis, and this is created by a point onto the plane and the direction of that point. So suppose that you are, for example, in the usual 2D Cartesian coordinate. This thing here tells you where to place yourself. In this case, it's the origin, but you can say, okay, let's place myself away from the origin, and then you give a principal direction. And this is the concept. It's quite immediate, so we can run it. In this case, we say that the point is going to be 110. The normal direction is going to be the y-axis, and the first direction is going to be the minus x and then plus y. Okay, so you can run it, and we create a rectangle. And as you see, the rectangle is going to be placed horizontal compared to the other one, and we need to turn around it to see it. Obviously, we can also do the following. So with a one-liner is already implemented the fact that you can use, instead of these directions, the predefined capital X, capital Y, and capital all the letters up to Z. Okay, or from X to Z. Okay, so this is fine. Just to give you an idea of what's going on, when we swap the directions, we can draw the union. The union is done using the plus symbol. Okay, so as you see here, okay, so just the plus of the 2 faces, you plot them, and you have these 2 different faces. Okay, and as you see, they are not centered. This one was the one from before, so this is the point 0, 0, 0. This was 110, so you have to twist it a little bit, this one, and then that's really it. That's really it for what's going on from the creation of simple things. Obviously, you have a rectangle, you have a rectangle centered, you have circle, many different things. To see all of them, you can go up and just wait a second, and just click on work plane and go to the definition, and you see that you have like different things that you can use. Okay, so you can go into the source code and really have an idea of what's going on. Okay, as I mentioned before, so the idea of the work plane is, suppose that you are in 2 dimension and suppose that you are drawing something. The idea is that how should you draw in a quick way? Well, we defined a 2D axis with a specific or a principal direction, H. And in this case, suppose that you start drawing from H, and I don't know, the analogy should be, suppose that you're driving your car and I give you some instructions. So at this point, you're like, okay, first step, drive for 1 meter and then sharply turn for 60 degrees. So you're drawing and then twisting 60 degrees and then drawing, and then you repeat this process 6 times. And then you extract the face. The face is everything that stays on the left of the line that you're drawing. Okay, and the thing on the right is the outer part, and you don't extract it. So this is exactly what you create. So you start from here, and you go for 1 meter, and you turn around 60 degrees, and you go, etc. And then you extract everything that is on the left. When I say something on the left, in the sense that you need to draw positively oriented, so mathematically positively oriented, so counterclockwise. Okay, So a second example could be, what about creating something that is a little bit smoother? So basically turn around, not immediately 60 degrees, but 60 degrees in total, and then you have an arc with a, you follow an arc of a circle with radius 0.5, and you can draw it, and you have this shape, okay? And yeah, this is not difficult to master, so take an example or create your strange shape, and then you draw immediately different things. Okay, so as I told you before, when you take a line that is counterclockwise, you extract, and you do dot face, you extract everything that is within this line. If you take something that is oriented in the other way, so reversed, you extract everything that is on the outer part. Okay, so if we have a work plane and we create a rectangle, and then we create a circle, but about that circle we create it with a, we reverse the orientation of the circle, and then we create again one circle and we reverse the orientation of the circle. When you extract the face, you will have something like this. Okay, so this is also quite immediate. So you created the whole rectangle, and then you added a reverse circle, and then another reverse circle. Okay, that's good. Okay, so for the 2D, basically, for the 2D plots, everything is done. Or to do 2D sketch is done. Let's try to pass from 2D on to 3D. So to do so, let's model something a little bit random. In this random thing, I created something that is called nice line. Okay, so just to give a name, and in particular is going to be one of the last lines. So when you create it in this way, we see that you can, I don't know, predefine a name for a certain line. This is going to be quite interesting into 3D. So we have our object, we can click on the things, we see that there is no name, but at one point we meet this thing here, and this is called nice line. Okay, why should we define names in 2D when we are creating objects in 3D? Well, when we extrude an object, or we rotate or revolve an object, so we create from a 2D a 3D object, based on the, let's say, hierarchy of the image, it will somehow spread the names that you predefine on the thing. So if you define the name on the line, and then you extrude the line, then the surface will have the same name. Okay, the same thing is going to happen for surfaces and volumes. So if you name a surface, I don't know, surface Edoardo, then the whole volume at the end is going to be called the volume Edoardo. Right. So let's play with it, or let's try to extrude it. Okay, the extrusion is going to be in a certain direction, so you can specify the direction. At this point, say, okay, -40 as magnitude, and it's fine. The other one is going to be a revolving object, and I skew a little bit the axis of the revolving axis. Okay, and if you click, I think it was in this thing. Yeah, you face nice line. Okay, so you have the name, the expected name. Okay, so almost done with objects in 3D. In general, you can smooth out your objects, or you can do a final, you can modify them at the end. So for example, the fillet, what it does, it's smoothen out the edges, and the make chamfer, or yeah, I don't know exactly how to pronounce this word, but basically it does something like a diamond cut. Okay, so this could be also helpful for you. All right. Construction of 3D objects. In this case, I just want to point out two basic names. There are obviously many more. So box, to create a box-like thing, and then you have the cylinder. So you just run these two. You can give names to the faces. In this case, the faces. You can modify and say, I don't know, edges, or just give the name to the thing, the object. You can use a selector, or this is called selector. So take the face with a minimum x value and call it cylinder min. This is on the cylinder. On the box you do the same thing, then you can fuse them together, and after fusing them you can create, I don't know, you can extract the faces that start with a box, okay, and end in whatever, so the regex expressions, and then you can predefine a mesh size, a maximum mesh size, and then you can just draw what's going on. So you predefine the mesh size, but we don't use it yet. And obviously here you click it, you have a name, you click here, you have a name, and that's everything that we've seen so far. Okay, so now we have objects that are shapes. When you have a shape, you can mesh it. We had predefined some maximum mesh size on some particular faces. We can obviously generate a maximum mesh size for the rest of the object, and we can specify also grading, so how fast it varies from one mesh to the from the mesh from one face onto the rest of the object. Okay, so let's just plot it, and you see that there is a certain grading, so the grading is very low. This is this face starts with box and then underscore under something. So this is gonna have a finer mesh, and this will have this has no name, so it's a coarser mesh. Okay, we can change this one to 1. Hopefully it's not gonna be too fast. Okay, so this one, you see that there is some change. This is a command that not many people know. When you run big simulations or big examples, you should use it, in the sense that you may want something. Just keep in mind that there is this comment or this flag. It could be quite useful. Okay, just let's go back to 9. Okay, now the idea is, okay, we have 2 different objects. How can we attach one object to the other? Well, first of all, we saw union, and union basically creates from 2 solids one unique solid. Then we have glue. Okay, with glue we have from 2 objects, one object with an interface, okay, in which we keep these 2 objects separate somehow, also in the mesh. So this is gonna be called the max box. This is gonna be called, as before, min box. This was the cylinder, and now we have that this is also called cylinder. And your question is, how does this glue together decides the name? Well, you can go back and you see that the first object that we pass is the cylinder, so it will keep track of the name cylinder first, and then it will add also the box, etc.
And if cylinder is default, then it takes the name of box.
Okay.
If it's cylinder not named.
Yeah. And what else? One thing I want to point out also, we can after we define the mesh, we can curve it. The number that you see inside here is the degree of the mapping. Okay, so this curve of the cylinder is going to be a 4th order curve in the end. Okay.
Polynomial.
Polynomial. Yeah, sorry, polynomial. Okay, so yeah, as I told you, be aware of the order of how you choose to glue the things together. One last thing that you may want to use, it would be the compound. Okay, the compound, basically, even the things touch each other, it in the memory it separates them. Okay, so if you run it, you can see that basically they are considered. Oh, I didn't twist it. Sorry. It does not consider them separate things, and as you see, the mesh overlaps. Okay, so I think that you can see max cylinder. No, okay. Yeah, the name I think is the same, but the meshing is different. Okay, so that's the whole thing. Obviously, in 3D you can transform your figure. So suppose that you have a certain shape, you can rotate it, you can move it, you can do different things. So this is an example. Okay, you start with this shape here, and then you move it to the side, and then you twist it. And yeah, if you are interested, you can go through this example. And okay, one few things. You can also give colors using these selectors that I mentioned you before. So you can take the face that has the maximum Z value, and you can color it with a certain color, and then another face with another color, and you have something like this. I don't know, impress your friends. And obviously, like, you can use the compound to select or extract a surface. This can be considered. Okay. One last remark. As I told you before at the beginning, we have 3 different layers. So we have OCC that you use to create these shapes, and then we have a NetGen that basically is able to get the shape. And NetGen, being a mesher, knows how to mesh the things. And then the last step is going to be to pass everything to NGSolve, because NGSolve knows how to solve PDEs. So we need to pass everything to NGSolve using the mesh. Okay, this class mesh. Okay. So why do we need to do mesh, or why do we need to use OCC in general? Well, just let me run everything so I can mention it. Okay. So the idea could be that you want to create metamaterials. How many of you know what metamaterials are? 1, 2, 3. Hey, all of you, more or less. Okay, so you want to create a metamaterial. They are quite difficult to model. So you start with a single cell, for example, and you want to, I don't know, to use this cell to create something bigger. For example, this one. Okay, in this case, what I did was to take this cell and then create a grid that is, I think, 6 or 7 times 4. Yeah, 4. And the idea is that if so this can be considered as a matrix, and if the index I plus j is equal, yeah, it's 0. It's an odd number. You do nothing, and if it's an even number, you basically mirror it. Okay. So as above, let's see. So divided by 2 is equal to 0. Otherwise, mirror. And yeah. Okay, then I give some names, I add some handles, and I extrude everything. So this is the extruded thing. And finally, I don't go through what's going on, but this is basically how we implement nonlinear elasticity. This is, you can give some number of steps, so follower loads, and you have your final result. Okay. So let's get rid of the edges, and you see that this is a metamaterial, so if you stretch it, it enlarges. Okay. Okay. So questions? Everything is clear? Good. Okay. Okay. So last thing, and then yes. Sorry.
If I run it, it says
change it to Paradiso.
Yeah, I know.
Okay, that should be.
This is by design, or like
Pack.
From source then, or like what is it?
I think did I call the function with pack? Let's go back a little bit. I think in Newton by default is pack, right?
Which version do you have? The very latest version, or do you have?
I think I have like installed 2 days ago.
Oh, no, so I don't have the yes, this was an issue, but I think it's now fixed. It could be that we have overseen it somewhere. Okay. So we have different default type solvers by availability. Not everything is available on every architecture. If you don't say anything, then it should pick the solver available for your machine. Could be that we had overseen it somewhere.
I think that was an old thing to have pack by default in Newton. I was old.
It was old, definitely, but
was old,
it's
yeah.
out and not 100% sure later.
Okay. Yeah. Okay. But we will see later on what to do with Newton.
So,
okay.
NGSolve update pre.
Okay. So let's give an example, and then we can have a little break. Okay. So let's try to work with these PDEs. So this is a condensate or a capacitor, and we have some Poisson equation with an epsilon. Epsilon depends on the mesh or on the domain. We prescribe some potential on the electrode, and we have a Neumann, the homogeneous Neumann boundary conditions on the exterior of the edge. We have two different permittivities, okay? So epsilon 1 and epsilon 2 on the air and on the electric, and I mean that we basically are working with this shape, okay? So in this case, this is black. This is not considered part of the shape, so the shape is this white air part, and then this gray dielectric part, okay? So let's see below. Let's apply what we have just learned. So we import everything. We create the outer circle. We name the edge of the outer circle outer. We name the face air, and we create different rectangles 1, 2, and 3 for the electrode 1, electrode 2, and the electric. We glue the things in the correct order. So basically, we take air minus the electric and then the electric, and then we subtract the two dielectrics. Okay, and then if we run it, okay. One thing that I did, I prescribed the mesh size for later purposes, and we just draw it, and here you can have fun clicking on things and see that they have the correct names, okay? Okay. All right, now what we do is, obviously we create a mesh, we pass to using OCC geometry. One thing that is a pitfall in general is that when you create from OCC to NetGen, you use OCC geometry shape, and you need to specify the dimension. If you don't do that, in this example, you can see that something wrong is going on. So please do it. This is not correct. Sorry, I forgot to change this. Basically, here what I did was, or I want to do, is to specify some material coefficient function. This is gonna change inside the updated version. But
this is an old style. It has 1 in the first domain, 2 in the second domain, but then you have to remember the ordering.
Yeah, the problem is that when you create a complicated mesh, it could be that the order change of the, so don't use this one. This is, otherwise bad things can happen. Okay, so anyway, like we plot our epsilon, and our epsilon has the following values. You can deform it and say, okay, this is 2, this is 1, as expected. You can query the mesh and look at what it does. We don't do that because we already know what it can do. Okay, we create our linear and bilinear form as before. So we create our space, we define an order is equal to 3. The Dirichlet on everything that is called L and then finishes in something, so electrode 1 or electrode 2. We create our test and trial function, or trial and test function. We create our bilinear form giving epsilon. We create our linear form, and this is going to be 0, so we just assemble it. It's not, I don't think that you need to assemble it since it's going to be 0, but anyway. And then we need to do something that many of you know. It's called homogenization technique. In this case, what you do is you suppose that your solution can be split into 2 different things. One is a 0 solution, so something that is 0 at the boundary, and the rest basically is an extension from the boundary into the domain of the Dirichlet condition, or the Dirichlet value of the boundary. And what we do basically then is this part here gonna get on the right hand side. We know the value of UD, so this is gonna be treated as a linear function. U0 is gonna be a minus 1 of the residual, and then the solution is gonna be U0 plus UD. Okay, so let's try to do this together. So as before, we create some boundary coefficient function. We prescribe some boundary on the 2. Yeah, obviously I forgot to run this one. Okay. Okay, I prescribe some boundary. It is already deformed, so this is the potential. And then we do exactly what I did in a more Pythonic way. So the residual, and then the A dot inverse on the Fridovs. and then plus equal because we can, and then we just run it. Okay, and this is gonna be the deformed thing. Okay, so this is the value of U. Okay, this is the potential, the electric potential. Okay, that's fine. Obviously, like as some post processing, we can plot the electric field. You can see that being two different things, you have sort of a normal jump or yeah, tangential jump inside the solution, and you cannot deform it for this in the same way that I told you before, because it deforms it in a planar way. Obviously, instead of using this thing here, you can say norm, and then you can deform it, but this is not so nice. Okay, as last thing that I want to show you is that we have some new tools, and I think that you will see a lot of, like you will see heavily use of it. And this is just how to create some field lines. Okay, so you can visualize what are the final field lines, and this is what expected. Okay, so inside you have an almost uniform. Yes, but let's consider only this part here. This is a uniform field, and on the rest is circulating around. And the one question that I had the previous days is why are not closed? Because we need to specify a length. Okay, so that's why they are not. What is it? We need to specify this length here. So this is not the up-to-date way to create field lines. I think that there is a newer one that was pushed yesterday.
Oh,
few days ago. Okay. Obviously, like I will polish a little bit, and then you can play around with this thing in a few days.
Some historic remarks. So when you have shown the field lines here, all of us were surprised. Well, field lines work in 2D. How did you find out? Then you said, okay, there was this tutorial from Jay 10 years ago. Yeah, imagine where very happy when they found this, and you had this example with the field lines also in 2D. It was very helpful here, but no one was aware that we can plot field lines in 2D. Actually, there was a bug, they were not really around, and yesterday Matthias could fix it. Now there are also smooth field lines.
So thank you, Jay. You saved the day. And yeah, so this is basically we applied everything that we just learned, and with this one I think that we can have a little break if there are no questions. Or no questions? Do you want a coffee? Maybe one coffee. Okay, so small break in, let's say, 10 minutes.
2:40 maybe, yeah?
Yeah, okay, at 2:40 we will group together. Right. So yeah, this one. These lines here. Upgrade them free.
And then they should work.
Probably if you just want to visualize visualization that for every single piece
I know all it can
You are the experienced talker. You reply to me by the way, I have news for you because I know they just started the mastering in France. I know all your colleagues.
Really?
All of them.
It's not that right.
That's fine. That's fine. I did my bachelor.
Yeah, I know.
So, like, for example, Nicola Francarola.
Non ho detto solo per
Ecco perché sei qua. Ti hanno mandato. Let's make you some more and then we can install. Okay. You play. One won't take, but yeah. Okay. How was the break? Good? For you following at home, how was the break?
Everyone came back.
Okay, then it's fine. Then it was good. Okay. So now we will start with our second part. The second part, as I mentioned, is going to be something that is not too advanced, but is necessary when you work with finite elements and in general when you do some computational math. We start where you can see here, like we have a preconditioner, adaptive, like some adaptive loops. We work in the complex field then, and then we show some time stepping, and then we see. Okay, let's start with some preconditioners. I'm not gonna go too much into details of preconditioners. I just want you to know that they exist, and I show you some examples on how to use them. They are okay. So this is a list of what you can use. So you have a Jacobi preconditioner and blocked Jacobi preconditioners. You can use direct factorization. You can use some multigrids, some algebraic multigrids, and then some BDDC for those of you that know what is BDDC. Okay, so let's start with importing everything that is needed, and then we have this nice example. So we have we set up a solve problem function. This solve problem function takes in a certain h, so certain maximum mesh size. We have our order, and we set it to 1. We set some levels. This is the levels of refinement. So if the level is 1, we do not refine basically. We have one flag that is called condense, and then we pass our preconditioner. The preconditioner needs to be passed with some flags. The default flag is the empty dictionary, and as you can see, the preconditioner are now selected from the module preconditioner. If we click on it, you can see the possible list here of preconditioners. Okay.
HQL images now is in there.
Yeah. Is import as okay, no, you don't import it as okay, that's fine. The default one is the diagonal Jacobi preconditioner, or also called the local. One thing that I want to point out, I will not tell you what this how this condense flag works, but in general it does a static condensation. Again, if you want to know a little bit more, in the iTutorials, I think is in 2. I can't remember. In the tutorials, you type static condensation and you will see immediately what you can do with it. In general, it does. I will not go into details. I will show you an example, but it's an optimization flag basically. Okay, so it takes a mesh, it creates a finite element, it has a bilinear form. In the bilinear form, you can pass this condense is equal to true flag for optimization, and then we solve our problem. One thing that we do is before we assemble our matrices, we need to define the preconditioner based upon this this bilinear form. Okay, so this is something that you need to take care of. So define the bilinear form, create the preconditioner based upon the bilinear form, and then assemble it. Okay, we have our this update method that you can use on your space and on your function GFU. I think that if you set auto update is equal to true, you don't need this too, right?
But yeah,
yeah. So at the beginning, yeah, you want.
And we are thinking of making this auto update default now.
Default is equal to true. When I mean,
you find the message space follows automatically.
So basically, here is auto update is equal to true. Okay, and if some of you want to try it out. Okay, and then we use our favorite iterative solver, okay, CG in this case. And as I told you, I will not go into details of how this condense works, but if you want to use condense, you need to do the first step, and then a second step, and then this third and fourth step. And this is how the condense work. Okay, otherwise you just take the inverse as usual. And the return is going to be the following. It's going to be the number of degrees of freedom and the number of steps that we used for this problem. Okay, to solve this problem. Okay, so I think that I explained many things. Okay, let's try to solve this problem with the default things. Obviously I forgot to run everything. Okay, so 8 degrees of freedom and then 4 steps. Now we can define, for example, our local preconditioner as our preconditioner as a local preconditioner, so Jacobi, diagonal Jacobi, and the preflex is going to be GS and then is equal to false, or the dictionary just the key is GS and then the value is false. GS stands for Gauss-Seidel. Yeah, you can run it and you can see that it takes a little bit of time, and then you have this kind of increasing, and you see that the number go like so it's proportional to the power of a number of refinements. Okay, we can also show for some other preconditioners, so the default multigrid preconditioner, you can plot it and you see that given a certain number of levels and fixing the value of the order to 1 in this case, you have that this basically converges to 8. In fact, like multigrid preconditioner is optimal in the sense of a number of steps, right? Okay. We can plot it just to see the difference between the two preconditioners. How long does it take, or not how long does it take, a number of steps and degrees of freedom for the local, so Jacobi and multigrid. So I now want to show you what's going on with these condense flag, and just to tell you that if you can use it, please. So here we solve the problem again, but now we change every time the number of the order of our space. So we start with 1 and then blah, 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 up till 9. And we see that somehow the number converges on the rows, so the last number, so it takes 2 steps, 4 steps, and 8, and then converges to 8 basically. And this one is blah, 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 so 5, 6, 8, and 8, still to 8. This one converges more or less to 13, to 16, etc. till 30. Okay, so if you increase the number of your polynomial order, you have some slight increase in the number of steps, as expected, obviously. But now what's going on if you use condense is equal to true? Can you guess? let's see, and you can see that the number of steps is globally bounded. Okay. Yes, as last thing I can tell you that there exists also this BDDC preconditioner. It's true that this is not bounded, but as you saw, it's really quick, so it's 0.4 seconds, 0.4 seconds, yes, and the other one was 3 seconds almost. So yeah, in general, like you can go to 2.1.4 to have more informations about this preconditioner. But I want to tell you that the idea behind this preconditioner is to have your finite element space. No degrees of freedom are coupled. Okay, so they are all free. The only coupled degrees of freedom are the one on the vertices of the triangulation. So you have that they are not coupled basically inside the along the edges. That's very fast explanation of.
It's a nice big chain. 214.
Can I click on it? I don't remember if
Okay,
no because it's okay. Yeah, okay. Okay, so this is as far as you need to know, for example, for preconditioner. So if you want to use it, use them. One more thing that it could be helpful for you, especially if you are working on your computer and you want to have a certain degrees of freedom, but you don't know how to place your degrees of freedom, is to use some adaptive refinement. So let's go quickly through this adaptive refinement. In particular, we apply a ZZ refinement or adaptiveness. So let's import everything. Yeah. And then in the geometry, we create the same geometry from the problem before. So this is the geometry. Before we were working with a few number of dots, and now what we can do is also the same problem as before. We have our bilinear form. We have our epsilon. So let's run this one. The problem consists. So solving a problem consists in a few different steps. The first one is to create a finite element space and update it. So if you already did a refinement, and then reassemble the matrix A, reassemble the right hand side, again reinvert the matrix, and redo this homogenization step. Okay. So we define this solve BDP, and we solve our problem, and we basically solve our problem in this way. Okay, so basically the idea behind is to do the thing that we did previously before the break in one function. Okay. Now it comes the important or the interesting thing. So how to declare some estimate. Let me. Yeah. Okay. Let's play with it. So in this case, we use a space for the flux that is an HDiv space. By default, I think is the BDM space, right? The HDiv is the BDM space. So let's see Douglas Marinier elements. What we do is the following thing. So we need to create an estimator, and to do so, we need the gradient of the function and then times epsilon, and this is going to be quite singular. Okay, it has jumps in the sense that before I showed you that the figure of the energy can jump from one interface to the other, and here we do an interpolation in our space, so it does not jump that much. So this is let's call it the true or the jumpy solution, and this is a smoother solution. And basically here we calculate how much is we give an estimate for the error, okay, for how jumpy or non-smooth our function is. And yeah, basically we can plot now the result, okay, and you can see that the error, the maximum error, is very close to the vertices. Okay, so this is in that vertex. And now the problem is, okay, let's mark, or yeah, let's integrate element wise. So we need to create this error estimator. So on each element, let's see how much is the error, and we see that there are a lot of errors that are really close to 0, and some errors that are close to 100 and something. So we need to mark them. How to mark them? We run over all the elements, and then we say, okay, on the mesh, we need to flag this particular element with this number or this particular element if and only if the estimator is bigger than a certain amount. In this case, the maximum estimator divided by 4. Okay, so we run it. We also give back the maximum estimator, the maximum error, yeah. And we need to say refine or mesh.refine, so automatically knows where to refine the mesh. We resolve the problem and we redraw the function. Okay, so this is one step. And as you see, so you can see that there is a little bit more of refinement here. Okay, so let's do the automatic refinement now. So we make calculate the error estimator here. Again, we update the flux, we update the function, and we basically do everything that we just did so far. This last line here may be interesting. So before I showed you that there is this loop that you have to do all over the elements. So this one here. Let me show you here. Okay, this loop all over the elements, and this is the vectorized version of the loop all over the elements, and to set the maximum error. Okay, so we create this thing here, we calculate the error, we refine, and then we also need to recurve the mesh. Okay, and then we create an adaptive loop. And how to create an adaptive loop? We create a maximum number of degrees of freedom. So up till the number of degrees of freedom is less than this amount, you need to solve the problem, update the level. If the level is divided by 5, so is a multiple of 5, we redraw everything, and then we recalculate the error, we refine the mesh, and then curve the mesh again. And then we can plot the problem. And let's go at the beginning of the cycle. So you can see immediately here that you have a little bit more degrees of freedom on the edges, or concentrated along the edges, a little bit more, even more, but now there are like other degrees of freedom that are spread on the other side, so on the other vertices, okay, on the vertices of these electrode. So many here, a little bit less here, but still. And then we go down. Okay, and this is the maximum number of degrees of freedom, and the maximum number is less than, so it's bigger than a certain amount that we prescribed, so it stops. We can plot also the error estimator, and we see that it goes down like 1/3 or 1/5, sorry, 3/3, so 1.5. And yeah, and that's really it. Before finishing this adaptiveness, I want to show you something. So you see how this is concentrated here, and this is concentrated here. And so far we said, hey, what about, why did we choose HDiv? Okay, so let's go back to the definition of HDiv in estimate, if I'm not wrong. Yes, here. So what about a vector h1 function? What do you think it's gonna happen from the theory? Do you remember? So in the theory, we use HDiv for a certain purpose, and the purpose is the following. So again, like we redefine the mesh, we refine everything, we mark the element, and we have some refinement, and you see that the refinement now it's done not at the vertices, where, by the way, the function should be singular, but it's done all over these other edges. But the function along the other edges is not singular. Okay, so there is something that is slightly wrong, and also the order of convergence is not anymore as good as the last one. Okay, and as before, you can create some field lines, and yeah, they are even better than before, but obviously with the naked eye it's difficult to see. Okay, and this is everything for adaptiveness. Do you have questions? Yes, please.
Can we run this on NVIDIA?
No, parallel. What could go soon is that you can do local refinement in parallel, but low tree distribution it's a longer horizon process.
Other questions? Yeah, please.
This auto update.
Yeah.
So, the vectors inside the data function would the length would change after you make a and just making sure that multi-dimensional data functions also have the vectors.
I've never heard that there was an issue if they are not automatically prolongated. If they are not automatically, it's an easy to add missing feature.
Okay.
But I'm not aware of a feature requested, but there's no principal problem with the multi-dimensional.
But that makes sense, right? Yeah, even for multi-dimensional data functions, we should have if auto update is turned on, we should.
And each component should be updated.
Okay, so this is everything for adaptiveness. If you don't have questions, so let's go on to Helmholtz equation. So in particular, some complex valued finite element spaces. Okay, it could be could happen that some of you have to work with some in the complex field. Okay, so let's suppose that we have our Helmholtz equation with a prescribed right hand side and a prescribed bulk or a prescribed frequency, and we have some boundary conditions. It's quite easy to implement this kind of problems in the complex domain. So in a quite Pythonic way, the imaginary value is called 1j. We create, as before, similar to before, I don't know, an easy example. So circle, okay, we name the boundary with outer, and we name the internal part with a scattering. And then we declare our finite element space just adding this flag, so complex is equal to true. That's it. And then you can solve your favorite problem. So we plot here the function. Just for plotting reasons, I lowered a little bit the value of the function, so you can see that this is an actual Gaussian peak. Okay. We form our system, so we need to declare our system in our problem in a variational formulation, and we can add the imaginary part inside here. Okay, so this is the first part is going to be grad the sec with the x, okay, because it's in this inside of the space, so on the whole volume. The second part is omega squared, there is omega squared, and then uv, and then the volume. And then the third part is going to be only on the boundary, and the boundary is denoted by ds. And in particular, it's not all over boundary, so it's not going to be also on the scattering part, but it's going to be only on the outer part. Okay. And we assemble it, and we linearize we create a linear form, and then again we solve it, and we can visualize it. Okay, so to have an animation that is immediately drawn this way, you can say animate complex is equal to true. Let's see what's going on without this command. Okay, let's see. Okay, so this is the result itself. Okay, okay, this is the final result. So we can look at the real value, you can look at the imaginary value, you can take a look at the norm. Yeah. The flag that I told you before, so animate complex is equal to true, what it does is the following thing. Takes the function, okay, gfu, multiplies by e to the power of minus it for some time, and then it let it run, and you see that. And this is the plot of the real part of that updated, let's call grid function or coefficient function. And yeah, obviously, like if you take a look at the real part and the imaginary part, it's going to be something like this. If you take a look at the norm, it's stationary. Okay. All right. So this is all that you need to know if you're working with complex things. one additional feature that you may use at some point is the fact that you can easily perform or you can add some PML regions, so perfectly matched layered regions. As before, or almost as before, I create a geometry and I added this PML region, okay, and I called it. I cannot. Okay, PML region. I called it, and in this particular case, I just to set a PML region, you go into the mesh. You say dot set PML. You give the first line is what kind of PML region you want it to be, and then on which part of the domain. Okay. To have an easy example, I said that this PML region I wanted to be a radial PML. And in particular, you need, being a radial, you need to specify a radius, a damping parameter, and the origin of this radial region. Okay, so just to see that it works, as before, we declare basically the same right hand side, we declare the same left hand side, and we run it. Okay, and you see that things are dumping. One thing that I want to point out is the following. This is a simple implementation, because usually in the PML region you need to modify your bilinear form, adding some other parameters, so you need to modify your bilinear form. In this case, everything is done within the mesh and within your finite element space, okay, that you declared, so you don't need to worry about anything else. Okay, and yeah, so this is it for the complex problems. Do you have questions? No? Okay. All right, so let's now. Yeah, go ahead, please.
I'm not sure what is in now. I think Lotte has used it sometimes recently, but I think the requests were not too heavy for this. Can you give a coefficient function for the profile test? No, but I think it would actually disappear. Yeah.
Either a small C++, I don't know, looking for it.
And also, I think that if you, let me go back to the set PML. Can you click on it? No, unfortunately, I cannot click on it because okay, it doesn't matter. I think that you have 4 or 5 possibilities to choose your PML region. One is like a brick form. The other one is circular or radial. The other one is, I can't remember, like you have 4 or 5 of them, and then there is another one that you prescribe what kind of transformation or what kind of region you have. But more than this, I cannot.
So the mainstream versions are easy to use. The advanced you can do with your transformation.
Okay, so let's maybe say something about the time-dependent problems. Some of you could be interested in. So let's start everything. We just play around with this kind of time-stepping problem. So we have a certain wind and we have a certain dispersion. Okay, the geometry this time is not interesting for reasons. So we basically recreate our square domain. Now it's not going to be anymore of length 1 but of length 2. We prescribe we define a finite element space with a Dirichlet boundary on the whole boundary. We prescribe a divergence-free wind. Okay, so this is the wind, and if you twist it a little bit, you see, whoa, goes all around. Okay. So, so for as a starter, I think that we could do a simple problem with an explicit inverse. How to do so? Well, we create we want to use our implicit Euler formulation. So to do so, we create our bilinear form A. We create our bilinear form M. we specify the time as just a float. You can pass other things inside, but for later purpose, we just see like this thing here. We create an M star. Okay, M star basically is created starting from the matrix M. For now, we require that these two matrices, they have the same sparsity pattern. We will see later on what's the sparsity pattern, but this is not, yes. So the sparsity pattern of a matrix basically is given by the how the degrees of freedom they see each other. Okay. So if you have a common degrees of freedom, you have a certain sparsity pattern. If you have another space, you have another sparsity pattern, but more on this a little bit later. Okay. So we created our M star. All the possible non-zero entries are these, so they are the same number for M, M star, and A. And to create our M star, we need to use this kind of trick. So you take the function and you take it as a vector. You take a function, you take it as a vector, and then you multiply it by a float. And then you can select the data of this vector in this way. Why do we need to do this in this particular sense? Because if you do something like this, so m star dot data, and then m dot mat, and then m dot mat, it does not recognize this thing here as a matrix per se, but it recognizes this right hand side as a dynamic expression. So as an operator, let's say. So this is a little bit abstract object, so expression object. Anyway, now that we have our matrix M star, we can invert it where on the degrees of freedom, and yeah, and we have it inverted, and then we use like just a Gaussian peak. Okay, and then okay, this is the Gaussian peak that you want to use for the we want to use as our right hand side. We need to define our initial boundary conditions, so this one. Okay, and then we need to declare a time stepping. So to declare a time stepping, we need the inverse. We need the initial condition, the time 0, the final time, the number of steps, and yeah. If there is an initial condition, we set it to the initial condition. There is nothing magical here. The thing that you need to take into account is how to define it in a more you can go through the code and you can realize that this is just the implicit Euler. Okay, so you have the right hand side, you multiply the m star by the residual, and in case I am I don't know, I have a certain counter divided by the samples. After a while, basically, I add to my multigrid function another vector, just for the visualization purposes. Okay, so this one, let's see how much it takes to run this example. 10 seconds more or less. Okay, and then we can draw our GFUT. Okay. By the way, one thing that I want to point out now is the existence of these multidimensional grid functions. In the grid function, you just use the flag multidimension, and with these multidimensional grid functions, you can add multidimension. So basically, you have repetitions of the same grid functions. That's
for eigenvectors, yeah, time-dependent snapshots.
For visualization purposes, it's quite nice. Yes. Okay, so the first part I showed you that you can take a matrix, somehow you can put together two matrices and invert it the hard way, and then you find a solution. The second thing that we can do is using an iterative solver. So for this iterative solver, you can actually do this thing here. So you create a matrix that is an expression or a dynamic expression matrix. You can create a preconditioner. For in this case, I chose this preconditioner. No reasons. Just to show you that you can use it. You can create some preconditioner for the M star matrix. yeah, let's run it. Okay, you can print what it is, and you can see that it's basically being a local Jacobi. Basically, is a local Jacobi with scale 1 and then multiplied by 0.001. Okay. Okay, that's it. We use our favorite solver. Oh, by the way, I don't know if you. Oh, I'll come to this later. And then we can run it. Okay. This is gonna be slower than the one before because we are using a CG solver on something that is not symmetric. So as before, I told you that there is the dispersive part that is symmetric, and then we have the wind, and the wind is non-symmetric. So you can play around with and modify so that you have a quicker solver, but it's just to let you know how to implement it using preconditionals. Okay, that's it. Took a little bit of time, but still we have almost, if not the same solution. Okay. Okay, at the beginning was quite boring, and I told you about these parameter functions, and now we see why they're important. Now we treat to treat the right hand side data, we need to declare a time. Okay, to do so we use this parameter function. As before, we create some function with a certain periodicity. So this is the periodic function that we want to apply. Okay, at each time step. The right hand side is going to be something of this form. So we declare Gaussian peak times something, and we see that the Gaussian peak time it itself defined on this parameter function. So it should be inside. Oh, I cannot see it. Ah, yeah, see, yeah, here. The time is here. Okay, so let's go down. And again, like we have almost the same problem. We have to remember to every time re-update our time. Okay, so time set, and then reassemble the right hand side, and then we have basically the same steps. So we can play with it. Okay, hopefully it's quick. And we basically, it's like dropping different solutions inside the spinning thing, and yeah, you have this thing. Yeah. Okay. Questions so far? No, I think it's, yeah, please.
For example, the same would work also for the bilinear form if it is time dependent.
I think so. You need to reapply the.
For example, if the time step is about meter.
Yes, then you reassemble it, and it takes a new time step.
Okay, and I saw in one of the example that there was also a flag called reallocate. What is the meaning of that?
You can reassemble a matrix, but it can store the same. It keeps the matrix graph. Okay. Typically, if the connectivity does not change. For example, for contact problems, when different elements come in contact, or say the matrix entries change, okay, then you need the reallocation of the quantity like that.
Okay. Okay. Other questions? All right. So, okay. As last thing that I want to show you is that you can also do time-dependent boundary conditions in the same way, basically. So you declare your initial coefficient function, or your your initial condition, or UD, sorry, boundary condition that is time-dependent. We set a certain time, and each time step basically we need to redo the homogenization process that we did at the beginning. Okay, so we do this thing here. The homogenization process basically is given in this form, and we just can run it. And this is nothing special. It's just, I don't know, I changed a little bit the functions from the tutorials from last year. So yeah, you can see that it does something. Okay, so this is, yeah. Okay, so that's it for, yeah. Okay, anyway, questions. So this is just how you implement time steps. Nothing special. No? Okay. Okay, do you want to do? Do you want to do the break now, or do you want to?
Are you?
And otherwise, I have last part of the.
No, sure. It's last part short.
It's like 30 minutes, 45 minutes.
So we have 30 minutes left, and so we can continue.
Yeah, that's okay. Yeah. Okay, now it comes something that is the core of NGSolve. Okay, so we have all these strange spaces to treat. So hcurl, hdiv, and then we can see some dg and hdg. Okay, let's start with the hcurl. This is going to be quite quick. I just point out the existence of different things. So let's run it for now, and then okay. Let's run also this one. Okay, so here I want to point out that you can visualize somehow the coefficient the base functions for h1. Okay, this is order 3, and as you can see, like we have these different orders. There are things defined on the edges, the things that are defined inside each element. So bubbles, and this is basically a loop. By the way, to visualize and to create these quads, I went at the beginning of the meshing and said, okay, quad dominate is equal to true if you need to use quads. Okay, this is an easy way to use it. Secondly, we can see, or we can take a look at what's going on for the hcurl, and for the hcurl we have these kind of functions, and you see that they are tangentially continuous. So if we stop for a second, and let's go onto the speed 0. And let's go here. Okay, here they are tangentially continuous. I don't know if I can find, let me see, could be that I can find some, we have, yeah, also here they are tangentially continuous. Okay, good. Well, if you want, you can play around with, take a look. And again, here you have functions for hdiv. This is the BDM. To have something different from the BDM, you can say RT, no, is it more equal to true, right? And here you should have the Ravier-Thomas functions. So just a flag to change from Ravier-Thomas to yeah, please.
I have like a related question. So you use this quad dominated equals true, but if you refine the mesh, it's not guaranteed that it's like, is it? Okay.
There are two different types of refinement. One is set by section, which I think will not work for quads. There's a netcam refine and NGSolve refine. The netcam refine should work also for quad. Uniform refinement should work also.
Okay. Because if you do this,
sorry, yeah. For quad.
And you do max h like much lower, do you then get
not necessarily. So in the square, I think that you still can have always quads. Inside other complicated shapes, you not necessarily you have the quads.
Okay.
When you want to have a square quad mesh, use make structured mesh.
Okay.
Because it's academic approach.
Okay.
And can I see if maybe here we can see where is it? Yeah, let's try quad.
Okay, it tries to build quads as good as it can, matching the given mesh size, and then maybe it gets something so here and
here you can see that you have quads, but sometimes you have triangles. Yeah. So it's dominated, it's not purely quads. Yeah, okay, yes. No, don't say it. Okay, so for now, just to visualize the functions, and you have like all these particular functions. How to apply this particular problem. So here I chose a quite advanced problem. I don't expect you to understand everything from this thing, but let's go through it together. So let's suppose that I want to find all the functions u, okay, that belong to hcurl, such that they are irrotational and they are perpendicular to the gradient of h1. So basically all the harmonic functions. And we know that on simple domains we don't have harmonic functions, so we need to play around with something that is not a simple domain. In this case I chose the torus. Okay, so we have an eigenvalue problem, or we can solve an eigenvalue problem, and we are looking for the lambdas that are zero. Okay, so I think that this problem was given, or you can find the same code in Sabine Zagelmeier PhD thesis. Okay, so did I? Yeah, sorry.
Not in Python.
Not in Python. Okay, so this is the double torus. Okay. As you can see, there are different things that you can do with the draw. Now you can also set some angles for the camera. Anyway. Okay, so I create or you can create H curl. You can print the degrees of freedom just to see if they are too much. You create a matrix A and a matrix M for the left hand side and the right hand side of your problem. You can create a bilinear form for the preconditioner of A, and then create the preconditioner. So as you can see, you can have two different things, but the important thing is that the preconditioner have the same sparsity pattern, and this has the same sparsity pattern somehow. And here to tackle the problem, the idea is that what if we use an iterative solver for this eigenvalue problem, and we let the preconditioner take care about the zero eigenvalues, or sorry, the non-homogeneous, the gradients. Okay, so we get rid of the gradients inside the preconditioner. So to create, so we assemble the matrix. We use this fast.create gradient, so this gives out the matrix that is the matrix of the gradient. Okay, it creates an H1 finite element space automatically. We create also the gradient of the matrix. We take the matrix for H1 as the matrix transpose.mmat.grad mat. We fix one point just to tell to the kernel that this is invertible. To the solver, sorry, this is invertible. We create basically something that projects onto the opposite of the gradients. To do so, you have the identity minus and then the projection onto the gradients. Okay, so this is orthogonal to the gradients, and then we compose it to have a projection. But the important thing, so this is not the important thing is not this part of the code, is this thing here. So you can go into the solvers and you can see all the possible solvers that you can use. And in this case, you have a pinvit, logpcg, and many other things that you can use. Okay, so ready to use, and then you can use it. Okay, and obviously I forgot to run this one. Okay. We have our solvers. It takes a little bit of time, obviously. So this is an iterative solver, so we can look at what's going on step by step. This is the lowest one, so the lowest eigenvalue. This is the one above, and then we keep increasing with the magnitude of our eigenvalue. And you see that, well, we can print it, by the way. So let's print the result. And you see that there are two eigenvalues that are 0. Okay. And these are the eigenvalues related to the harmonic functions, and then all the others are not. So let's basically here maybe I can tell you a little bit. So our grid function works in this way. You have a multidim, and then you can select how long is this multigrid, so that you can store some space, and then you say, okay, gfu.vex.I, so the ith column, and then select the data and give the data that we just found, and then draw it, and then it draws automatically. So as you can see, this is the first eigen function, and this is irrotational. And now let's go to the second eigenvalue that is irrotational, multidim, and then time 1. Okay, this is it. And this is the second irrotational. And then you can animate if you want to have fun. See something else. Just nice to look at, not that meaningful. Obviously, if we rerun it once again, we could have a different results. in the sense that you know that let's wait a little bit, and let's hope that this one gives us a different result. Yeah, as you can see, it changes from the other one. Why? Because this is how solvers work, in the sense that you have some random effects, so it can choose it's a combination. So if you look for the correct result, is a combination of the two eigenvalues that point to the same exact eigenspace. So you work with eigenspaces, not with eigenvalues.
The iteration starts with a random vector.
Yeah. Okay, this is what you can do with the hcurl, for example. With hdiv, well, we already saw that hdiv per se alone is not that it's not such a curious space, but you can, using hdiv, you can do a lot of stuff. So for example, the mixed formulation of a problem, okay? So you know that's and many other things obviously, but let's focus with the flux problem. So we have our flux problem, we have our primal formulation. For our primal formulation, obviously you have some natural boundaries, you have some essential boundaries. Now let's recast it in a mixed variational formulation. So do you say that the flux is equal to the gradient of something, and then basically you can recast it to the mixed formulation, and you see that the value of the essential boundaries and the Neumann boundaries, they change. So take care about that thing. And as usual, since you have a bilinear form written in this way, you can somehow put everything in a more compact, big bilinear form, such as this one. And with NGSolve, you just need to write this one here, and it takes care of everything else. So what's new here? Well, you can we use the domain as before, so you see that the results basically are the same. We curve the domain, so this domain is our favorite. We create our coefficient function. We create our product space. The product space is just the normal product between two different things. Okay, so this is it. Just to notice, you have for hdiv one order, and for L2 one order less, but this is for later purposes. And in particular for hdiv we have our Dirichlet conditions. Okay, that before were Neumann conditions. Again, our trial and test functions are written in this way. We have several other coefficient functions that I did not go into, but for example, one is the normal coefficient function. If you go into special coefficient functions, you see many different ones. Here you specify the dimension of the mesh, and then you can print the normal, and you see that this is real, dimension 2, normal vector. Okay, so again, we need to define our boundary coefficient functions. The bilinear form is given as I mentioned before, so you put everything in a one-liner. The right-hand side again, and you put it in a one-liner. You use the S in this case. You name the components of your functions, or of your GFU, or in this case GFN, as a sigma and u. Okay, so you need to interpret. Let's go. Okay, when you create a grid function, is a grid function that has two components: the components for u and the components for sigma. So you need to split them in the end. So let's okay, run this, and then finally we have, yeah, we inverted you knowing how to do it. Okay, and this is the continuous part, and this is the L2 part. Okay, and you can see that this is of order 1 in this case, so you can also deform it to have a better view of what's going on, and this is what you expect. Okay, piecewise continuous, piecewise constant. Okay, now this is a trick that my students learned in class. This is a post-processing trick in which you can go from basically P1 or P0 approximation to a P2 approximation. I'm not going to go into how to do it, but yeah, basically it's a minimization error of the energy, and this is the solution. Okay, so from P1 from L2 elements of order 0 to L2 elements of order 2, and in this case you can zoom in and you can see that they are still L2 elements in the sense that they are non-conforming. And yeah, and with this one you have shown you a little bit of HDiv. Do you have questions about it? This is per se just an introduction on how to create mixed problems or how to put together different spaces. Just use the times. That's it. Okay. Okay, so let's maybe talk quickly about the DG and HDG. How many of you use DG on the daily basis? 1, 2, 3, 4, 5. HDG? 1, 2, 3. Okay, then let's go through them. So discontinuous Galerkin, you know that's how the formulation works. So basically you have a jump term, you have an average term, and you need to consider things that are discontinuous somehow, but they know what's going on the other side. Okay, and how to do so? Well, it's quite easy. So let's create one shape. Okay. By the way, I'm not gonna go into the details of the bilinear form, but this is the linear form that we need to implement somehow, and this is the other part of the bilinear form that we need to implement if we have a wind. And yeah, we create a shape. This is our shape. Okay, something. And to create our DG function space, you just use DG or DG jumps is equal to true, and that's it. And that's really it. You create your linear and bilinear, try and test function. You create your jump. How to create your jump? I told you that in this DG formulation, if you have a function or if you're on an element, you know what's going on in your surroundings, and to do so you just say u dot other. Okay, that should. You have your normal function, okay, and special function, and then you can create your mean value with gradient u, gradient v of other, and then 0.5, and then times n, and that's really it. Oh, yeah, please.
What are these objects? So this mean, this.
Okay. So these.
You mean as a type in Python?
Yeah.
As a type in Python?
Yeah.
This is our. Let me see what they are in a written as form. Coefficient functions, I think. But
print mean like this.
Yeah, coefficient functions.
So it's u minus u dot asa, and the u dot asa are proxy functions. U is something undefined. It's an argument for the binary form. It's a proxy function, and u dot asa is also a proxy function, and it knows that you don't use the integration point from the current element. You use the integration point on the other element.
One thing that I may tell you is that in NGSolve itself, it knows which one it is. So you have two elements, okay, that are close together, and you basically are working on the face, on the interface. Then you need to define a master element and then subordinate elements, let's call it, and that's it. So the other knows, or the U knows what it is, and the other is not the master, basically. Keep in mind this thing, and then we will see what's going on from the sparsity of the matrix, okay? Okay, so two things that I want to point out is that now, since we have to travel basically across the interfaces, instead of using dx and that's it, we use dx and then skeleton is equal to true. So what this tells you is that you need to create a force cycle on the interfaces. If you don't, then what's going on is that you basically stay on an element and you look around at yourself and you guess what's going on. And then you change element and then you look at the interfaces again. Okay. So you need to remember when you use DG, skeleton is equal to true. This is important. If you don't do it, then I think you have an error or...
no, there are two ways how you...
no, but the other way I want to show it in... there is the second way that I will show it. Yeah. Okay, so the binary form is the one from before. You just write down all the things, remembering that you have a skeleton is equal to true. You just run it. You have a right-hand side. You run it, and then you have to invert everything and and to create the solution. And this is the solution, a beautiful solution. Okay. So let's open up the deformation. Okay, that's the solution. How to do DG, and in fact they are DGs, and if you zoom in you can see that they are somehow non-conforming. Okay, so okay, so I told you before that the DG, it's different from the NL2 because it needs to require the knowledge of what's going on the opposite side of the interface, and if we print the possible non-zero entries, there are way more in DG than in L2. Okay, and in particular we can plot the sparsity of the matrix, and this is the matrix for DG. Okay, so you see that there is a diagonal thing that is full. It's basically each I don't know if to explain it. Okay, let's. So basically, you have this full diagonal, and it means that in each degree of freedom can touch all the other degrees of freedom close to it. Okay, so let's say that you are on a vertex, then the vertex can touch all the degrees of freedom.
You have L2 spaces.
So you have L2 spaces.
Only this
only the cells degrees of freedom. Sorry. Only the cells degrees of freedom. So no, not the vertices, but the cells degrees of freedom. Let me show you what's going on, for example, for L2. Okay, this is for L2. So L2 does not see the other degrees of freedom.
No interaction is
no interaction across interface. Yeah. So okay, then you can print also the H. By the way, I forgot to say that H is also a special function. This is the mesh size, so it takes the mesh size on each element. Okay, suppose that you want also to add a wind. To add the wind, we need an upwind scheme. For the upwind scheme, we use if pos. If pos is the same thing of if positive. So if positive checks if this inner product is positive. If it's positive, then it uses this one. Otherwise, it uses u other. And this is exactly what you do for the upwinding. And yeah, you just need to click this one. You use Paradiso, and this is the flower blown away by the wind. That's it. Let's see if I have something else. Yeah, I can plot the sparsity matrix, and yeah, also here you have some sparsity of this form. Yeah, and this is everything from the DG perspective. You have questions?
This was to loop over the edges.
Yeah.
You can loop also over the elements, and you just write dx. It's a normal is always from the current element, and you can look into the other.
This one, yeah. Okay. Okay. So let's talk about hybrid DG. Again, the same shape, the same setting. Now what we use is just L2, and we have some facet space. So as you know, in a hybrid DG, you need to have a finite element that lives only on the, let's call it skeleton or subspaces or subsimplices. Again, we use the product to define the product between the L2 and the facet space, the try and test function, and here we define the jump just in this way. Okay, so we don't need u other because each element does not know what's going on the other side. Okay, so again, we define the right hand side in the same way. We need to define the x as element boundary is equal to true. and this is the difference. This is the difference from the other part. So if you use dx of the boundary is equal to true, it makes a loop over each element and basically looks at the boundary of each element, and that's the only difference. And again, basically it's the same thing. I told you you can use these condensed flag to have some optimization. Let's not go through what's going on. And this is basically the same result as before. Okay, so works almost in the same way. By the way, you can now plot the matrix, and this is the power of HDG. And if you plot the matrix, you have 4 parts, or let's say 3 parts. And this is the matrix for L2, I think. Yeah, because L2 was called before. And then this is the mixed part, and then this is the HD part. Okay, now this is the sparsity matrix that you see. One thing that I want to show you what's going on if you say condense is equal to true at the beginning. Where is the hours? Yeah, condense is equal to this condense are true. Okay, let's run it. Now the thing that we have in the end is this element here. Okay, this is I told you I don't want to explain what's going on, but internally basically it takes to create this sort of matrix. It takes this bottom matrix, or bottom left matrix, the top right matrix, and this matrix here, inverts this one that is easy to invert, and then multiplies by the left and the right by these 2 matrices, and it condenses everything into one small matrix. And basically we use only that one in the end.
Onto the skeleton.
On the skeleton. Again, if you want to learn more, please go into the tutorials, and it's well explained. But okay. Some remarks on the sparsity. Basically, this is the difference between the skeleton is equal to, so the actually numerical 0 versus the reserved entries. And as you can see, you have a master here, a master element versus a non-master element, and you basically put all the informations into the master versus non-master part. And yeah, this is the first thing that I want to show you. The second thing is, yeah, if you say DG true versus this is DG false, as I showed before. Okay, and that's it. Yeah, this is quite advanced stuff, but you can basically have so these 3 patterns that you see is when you say p is equal to 0, you higher the number of p's, and you see that depending on what mesh you have sometimes a repeating pattern somehow. To have something that is similar to the first pattern, you can say all degrees, all dots together, and basically what it does is instead of saying, okay, now create me the all the vertices, and onto all the vertices, so take all the vertices first, and then take me all the edges, and then take me all the interior bubbles, take me on from the first element everything, and then from the second element everything, and then from the third element everything. And this is how the degrees of freedom are built from the performance point of view. I think that one is a little bit faster for.
Yeah, with DGs there are many possibilities how to use it. Do you want to build the matrix? Do you want to apply the operator? Do you want to do it matrix free? There are more assembling strategies possible how to do it.
Okay. All right. So let's look together at the last thing to learn. Okay, non-linear problems. Okay. So suppose that you want to solve such a problem. This is a non-linear problem. So to do so, usually you need to declare some Newton stepping, and for declaring the Newton stepping, you need to know the first variation or the derivative of your function. Okay. So fortunately, NGSolve gets it's quite helpful from this point of view. So let's create our. It's not properly bilinear. Is a form. Okay. It's multilinear. No, it's not multilinear. It's multiform. It is not such a good name. So okay, just call it bilinear. It's called bilinear form. It could be non-linear. Okay, so we set Dirichlet, we set some order, we have our bilinear form. This is not a bilinear form, and now we need to implement somehow a Newton method. To implement our Newton method, a quickly reminder, you need to do a few things. So first of all, you need, let's go on to the method that is a little bit easier to do. So you need to start from a certain point, and then you need to compute basically each thing inside this line. So first you need to compute this matrix here or this derivative here at this point. Then you need to know what this thing here. Then you need to solve you need to do this computation here. This should give you a vector as a result. You need to put it on the other side, and then you need to invert this thing here. Okay, we can do all these things together. So basically you have this residual part is basically given by something that is called apply. So the a dot apply gives you back a vector. To create the matrix B, you need at a certain point, so this is the derivative to us at a certain point is a dot assemble linearization, and then you need to give the vector onto around which is linearized. And then finally you can invert it using your favorite method for inverting it. Okay, and then obviously you give a certain criteria. Okay, so far I think we have questions. I showed nothing, but I also forgot to ask you if there are questions from DG. No? Okay. Okay, so let's create a simple Newton as before. So we create a residual, we create the delta U. We have some finite element space, obviously. We have some the apply. Okay, so the apply basically takes in this GFU and gives you out the result as saved in the residual, assemble linearization, and then we invert everything. And then let's run it. And here I have a simple Newton, and it converges in 4 time steps, and we can print it and we can animate it. So as you can see, it changes slightly. Well, it changes a lot from the time step 0 to time step or to the step 1, and then slightly, and then you don't see any difference. Maybe from the top you can see some difference for this one. Changes a little bit, and then that's it. Okay, so fortunately NGSolve gives us a Newton method that is already implemented. You can use it, and as an example, as an example, we try to solve the stationary Navier-Stokes, and in this case you have this nonlinearity here that you have to take care of. So you implement everything inside this bilinear form. By the way, I don't know if you've ever seen this part here. This is a Lagrange parameter in which mu is just a number, okay? And this is why we need to use a finite element space that is called the number space. And this is the integral on P, and basically tells you I want the mean value to be 0 of this function.
Is Amstec you need it, but he's not, or vice versa?
Yeah, we use this.
You use this, right? Okay, so let's basically what we want to solve now. It's a driven cavity problem. So you have this square, and you have something blowing on top, or a certain velocity on top, and you see something rotating inside this thing. So as I told you, you have now the product between 3 different spaces, the vector space H1, then H, and then number space, and everything is as before, really everything. And then you can basically set your 0th coefficient function, so the velocity, to a certain value, and then we can use a solve and visualize. If the dimension is equal to true, so we create the function to solve everything with our simple Newton, and then we use solve and visualize, and we see that in 4 Newton steps we have our solution. Okay. one thing. This is the this is basically the printed solutions at each time step. Okay, anyway. Okay, now we decide to lower a little bit our viscosity, and then you see that it takes a little bit more time to have a solution, and even more, and then even more, and then at this point you see that here does not converge. Okay, because we need our Newton was too far off our the correct solution, so the initial guess was not correct. Thankfully, NGSolve provides with the Newton function, and the Newton function has a dump factor inside, and we can run it with this dump factor, and it should converge in a little bit longer. Obviously, it takes a little bit more time to verify it, but still it converges. So this solution is correct, and we are really happy about it. Okay. Obviously, there are some PDEs that needs to be solved using Newton because they are functions, etc. But what about trying to solve problems that are functional problems? So let's suppose that you have this functional E or energy of something, and then we want to solve it. Even here, there is this variation keyword that allows you to take this thing here and to derive it. So using the variational form, using the first variation, and it pops out immediately this object here. Okay, so you don't need to take a pen and paper and to derive it. And NGSolve is so kind to provide us with this variation, and then automatically pops out this thing here. And in particular, let's use it. Let's use it here. So to the bilinear form, what we want to add is just the variation of this huge object here. And as you can see, you just need to pass u as a trial function, and automatically it creates also the test function. Okay, so good news. We can just run it, and then we can just use a Newton solver, or you can use a Newton solver, or else you can start with your bilinear form from before and use a Newton minimization, and then you have the same result as before, because obviously. Okay, and then that's it. Do you have questions? I think that this was quite straightforward. It's just that I tell you that there is Newton, you can use Newton. And obviously there are many more functionalities. You can click on solvers and look at all of them, as I told you before. The min res, and I don't think that there is much more to add. Questions? No? Okay, now you give me 5 minutes and I show you the example from the beginning, and we can go through it together, and you realize that you learned everything now. And okay, let's go into dynamics. So here we import everything, and here we have our time dependent method. Okay, so you have the second derivative, the acceleration, and then all the other things, and we don't really care what are the other things, because we know that you can use a variation then. And then we create our geometry, name the geometry. We create our Cauchy green tensor. We don't know what it is, we don't care too much. We just know how it's done, and then we decide some Lamé parameters, and we know that this is rubber. Okay, so this, you open a textbook and say, okay, the parameters for rubber, okay, and these are given. And then we say, okay, this is the Hookean energy that we need to take the first variation in the end. And this is the space that we need to create. And this space is, this was an example from my class, or an exercise. And we need one function that is basically the dislocation, or it's called, not, it's not dislocation, is I have a lapsus. Displacement. Thank you. Sorry, is displacement. And then I have Q is the space number. So basically, what I'm telling is, I want to lock the average displacement on the bottom of our pendulum, but I'm not specifying the momentum, okay, of that object, so it can basically swing around. Okay. Then I need to choose my favorite time-stepping method, so I need to create obviously something that stores the result in the futures and something that was in the past. This is quite okay. Then I have my bilinear form and I have to solve for UN. Okay, so this is the this unknown, and to do so I say, okay, this is my bilinear form. I use my variation over this thing here. I use .compile because simplifies a lot. I use the inner product of U and P, so as before, as I did before for the formulation of the nonlinear problem here. You realize here. So this, sorry if I'll show it again, but maybe I ran a little bit over this point. So this one here, okay. So I need to block this thing here. So is a Lagrange parameter. Yeah. On the stop, I choose my favorite scheme. This is a numer scheme. I implement my numer schema, and then what I do, I require, or I call Python. I create a multi-dimensional object, and every time I append what I need, and at each time step I use a Newton. Okay, and I here just for show I can do it true, and I can show you that. What did I change? This is that's false then. Yeah. This is 16 seconds, should be around. Okay. If it converges.
You've seen it before.
We've seen it before, otherwise I will open the... Okay, so, and then here is the result, and we saved it in a multi-dimensional thing, so we can implement the animation, and the animation is what it is. And you see that's... Yeah, and we used almost everything from what I explained, so hopefully the full cycle is complete. All right, thank you very much. If you don't have any other questions, thank you for the attention.
Thank you very much. It was a good start, a good crash course around many features of NGSolve for newbies, and also for people who have used it some aspects and have seen maybe different aspects.
Yeah, in the upcoming days you will see advanced things, so it's good that you had you went back to the origins of...
This was a sampler across many features. Tomorrow we focus on more specific topics, solid mechanics, fluid dynamics, also with some advanced algorithms. Okay, so
now we drink another coffee.
We have seen now, and I think
okay,
not more to add for the session. So catch up. Okay, we have now the meeting in the evening again. I think 7 o'clock. The restaurant Wien, it's walking 10 minutes from here, or takes the time.
So it's like 15 minutes walk.
Yeah. So, yeah, I think we are some of out of the course. I say here you can stay here with us for the time to the dinner, or you have a walk around and
you have Vienna or problems in NGSolve. It's a good time. There's the next hour or so. There's a lot of people around that can help.
One more thing. David answers